All right, so this little section here ties in our work with our polar coordinates. Okay, and not surprisingly, it's the whole topic is just changing our Cartesian form of a complex number into a polar form of a complex number, which we call is the modulus argument form. So thinking of our polar coordinates, our polar form describes our complex number in terms of its distance from the origin and the angle it makes from the x-axis, or the real axis in this case. So again, the adjacent side, r cos theta, the opposite side, r sine theta, okay? And so my imaginary component, r sine theta, my real component, r cos theta. So that's our starting point. The distance, r, a squared plus b squared square rooted from Pythagoras' theorem, mod z. So the r is the modulus of z. Theta, the angle we make from here. So opposite over adjacent. So we involve tan theta there, isn't it? So as we get through, the angle we make is called the argument of z. And that argument is defined, and we'll see that next page. The argument of z is given by tan theta equal to y on x, which is the imaginary on the real. So theta equals tan inverse of y on x, all right, which is all from our polar coordinate stuff. Now we'll talk about what we're talking about just in here is if we're talking about an angle, and remember, if I want to talk about that angle there as 30 degrees, well, that angle of 30 degrees is 30 degrees. It could be 390 degrees. It could be negative 330 degrees. There's an infinite number of ways I can represent that angle. All right. So what we do instead is we talk about the principal argument of z, and that's an angle defined between negative pi and pi. So if we think about our Cartesian plane, or our should have gone blank. Argand diagram, got there eventually. Our Argand diagram, if we have from positive pi inclusive all the way around to negative pi not inclusive, we cover all the angles. So my principal argument of z has to be the angle between pi and negative pi, all right? Which is what we're saying there. And we can see here a whole range of different complex numbers written in polar form. So 2 cis pi on 3 means we're a distance of 2 from the origin, and we're an angle of pi on 3 from the horizontal axis. Cis negative pi on 3, radius of 1 from the origin, angle of minus pi on 3. So notice it's negative pi on 3. You could argue we could have been 5 pi on 3. But the angle's outside the domain that we're wanting to reference, so we always keep it within. So really from, I guess, theta equal to 0 at the horizontal, anti-clockwise back towards pi, or negative pi, for the bottom half of our axis, and then anti-clockwise heading towards pi is our positive angles. All right. What else do we need to discuss there? We've touched already briefly about how the angles may not be unique, and so that in fact then our angle we get right between negative pi and pi inclusive. All right, so that's what that's all talking about there. And my angle, okay, tan theta is opposite over adjacent, which is the imaginary over the real. All right, and this is just sort of, I guess we'll talk about that. If our quadrant, in the first quadrant is our angle. So in other words, if we're there, we can just do tan theta of imaginary over real. But if we're here, we need to think about the quadrant that we're in instead of just going with. Because don't forget, typically if I just do tan inverse of, if I've got 1 plus I here, tan inverse of 1 plus I would be 1 over 1, which is pi on 4. Fair enough. But if I'm at minus 1 minus I, tan inverse of minus 1 over minus 1 is also pi on 4. So they can't both be the angles of pi on 4. So instead we've got to take into account we're over here. And so really theta is negative 3 pi on 4. All right, so we'll talk about that a bit more now. All right, find the modulus and the principal argument of each of the following numbers. So we'll just set it out as we remember that z is equal to a plus bi. The magnitude of z is equal to the square root of a squared plus b squared. Theta, the argument of z, is equal to tan inverse of b on a. All right. So 3. So obviously b is 0 in this case. So the magnitude of z is just the square root of 3 squared, which is just 3. Now we can think about it. So theta, tan inverse of 0 on 3, which is tan inverse of 0. So theta is equal to 0. And that kind of makes sense. If I just plot the point 3, which is there, the angle is 0, isn't it? So I write this as, I'll just put it, we write that as 3 cis 0. That's what that complex number is represented as. All right. Negative 4i down here, same principle. Let's go with mod z is the square root of 0 squared plus negative 4 squared, which is just equal to 4. Tan theta of b on a, which is undefined, isn't it? Okay, negative 4 on 0 is undefined, so we know then that theta is equal to, well, pi on 2, but we check to see where our point is, and my point is here. So in actual fact, theta will equal negative pi on 2. Because I'm starting there at 0 and moving in an anti-clockwise direction. So here, z is equal to r, which is 4, the distance. And then the cis theta gives me the direction. And negative pi on 2 tells me I'm sort of down to negative pi on 2, a distance of 4 away. All right, 2 plus 2i. Where's 2 plus 2i? 2i out there somewhere. That's the mod z. So the magnitude of z is equal to the square root of 2 squared plus 2 squared, which is 4 plus 4, which is root 8, which is 2 root 2. Tan theta is equal to y on x. Therefore, theta is equal to pi on 4. Check my quadrant. Yes, I'm in the right spot. So therefore, z is equal to 2 root 2 cis pi on 4. All right, I hope we're getting a feel. Magnitude of z, square root of a squared plus negative root 3 squared, square root of 1 plus 3, which is 4, so it's equal to 2. Theta is equal to tan inverse of y on x, so I don't worry about the signs, I just get the angle. So what's tan inverse of root 3? That's pi on 3. Which quadrant am I in? Where am I? 1 minus root 3 is 1 minus root 3, which is down here. So theta is obviously equal to negative pi on 3. So Z is equal to 2 cis negative pi on 3. So there's my polar form. So that's a really key skill. If we can work with getting our complex numbers from Cartesian form into polar form, that's a massive skill for us. A couple of things to note. If we're looking for the conjugate of a complex number, you think about the conjugate, it means the imaginary part changes sign. So if that's Z bar, so that's theta. So the only thing that happens is my angle changes. So if Z is equal to R cis theta, then Z bar is R cis minus theta. Converting Cartesian form into polar form is just continuing with what we've been doing. All right, so let's just work through these. In fact, this is a great opportunity to pause, work through, and have a go yourself. All right, hope you've done that. Let's have a look. So Z is equal to the square root of 1 squared plus 1 squared, which is equal to root 2. Theta is equal to tan inverse of 1 on 1, which is pi on 4. Always check my quadrant. I'm there. So pi on 4 is my angle. Z is equal to root 2 cis pi on 4. All right. Minus 1 minus I. Z is equal to square root of negative 1 squared plus 1 squared, which again is root 2. Theta is tan inverse of 1 on 1, which is pi on 4. Check my quadrant. Minus 1 plus I is there. So that angle there is pi on 4. So my angle there is 3 pi on 4. And that's what we're sort of talking about. Therefore, Z is equal to root 2 cis 3 pi on 4. So you've got to check which quadrant you're in each time. All right, a little bit messier, but same process. Z is equal to the square root of negative 1 on root 3 squared plus negative 1 on 3 squared equal to, that's just going to be 1 on 3, and 1 3 squared is 1/9, so that's equal to 4/9, isn't it? Which is 2/3 the square root of that, so a little bit messy. Tan theta equals y 1 on 3 over 1 on root 3. So tan theta equals 1/3 times, flip it upside down and multiply, which is equal to root 3 on 3, which is 1 on root 3. So theta as an angle is pi on 6. Check my quadrant. They're both negative, so it's negative, negative down there. Pi on 6 is that angle there. So negative 5 pi on 6 is my argument. So I'm going to have Z is equal to 2 root 3 cis, what did I say? Negative 5 pi on 6. We can do all these on our CAS, and I'll put a screenshot of that in now. A couple of things you see up here with the printouts. The calculator doesn't give it to us in Modulus argument form. They give it to it in a Euler form or Euler form, but it's got the same key features. The 2/3 there is my magnitude. The negative 5 pi on 6 is the argument. Okay, so if we compare question 1, root 2 mod pi on 4 the angle, root 2 mod 3 pi on 4 for question 2, and then 2/3 and negative 5 pi on 6 is the angle. Okay, so it does give it in a different form. It's an American version, Euler form. Not too sure why we don't use it, but we don't. To access that command, if you go to number, so actions, number, and then you select complex tools, and you'll see convert to polar. Okay. If we want to go the opposite way and convert our polar numbers into Cartesian numbers, reverse process. So don't forget that that expands to 2 cos pi on 3 plus 2 sine pi on 3i. Cos of pi on 3 is what? A half. So 2 times a half plus 2 times root 3 on 2, which is equal to 1 plus root 3i. So it really is just expanding. Cos 2 pi on 3, 2 pi on 3i, thinking about quadrants, so that's the second quadrant where it's negative. So negative a half plus positive sign there, sine of pi on 3 is root 3 on 2. 2, might be easy to leave the plus sine of negative 3 pi on 4. So clearly they're not exact I. We don't know those angles. Oh yes we do, what am I talking about? 2 times cos of negative 3 pi on 4 is third quadrant. Cos of pi on 4 is 1 on root 2, negative. In fact, I might write it as root 2 on 2. Negative 3 pi on 4, third quadrant. Sine is negative. Also root 2 on 2i. Then if I multiply my 2 through, I get root 2 minus root 2i. Again, similar sort of thing with our calculator. We can do it on the CAS. And if we see, I guess, it's a bit not the greatest position for it, but there's the complex number that we put in. And the easiest way to put it into that form is to copy paste that expression that's already on your CAS. You can go to e to the power of I pi on 3 times 2, but I find it easier to copy and paste an existing complex number down and then just replace it. So there's our 1 plus root 3i, our minus a half plus root 3 on 2, and our minus 2 minus 2i. So converting from one to the other, really important, and it takes some time to get comfortable with the terminology in the process.